have any effect on a voter's mind at this point? No, there's reason to believe it really doesn't. Most Americans have made up their mind. So, he'll have to go out and respond to these things when they happen. But it's not as if those reports single-handedly are going to move the needle one way or the other. If anything, it might just inspire people to show up to either vote for the president because they're sick and tired of hearing about what he said in the past, or for Biden because they're sick and tired of hearing about what the president said in the past.
You bring up a really good point, Ed, about
I posted the link in the to the YouTube video streaming, and here in chat and also in announcement. It's also in your email. I'm going to the YouTube streaming for this lecture because I can get the better sound there and better video, and I can also keep it recording on YouTube rather than on Blackboard, which is really difficult to upload, and I get really bad videos there. So I'm gonna use YouTube streaming. You're not gonna be able to talk back to me, but you can write your comments in YouTube on the side if I can, you know, see that. We'll talk more about this tomorrow. So that's what I'm gonna do. So we are going to talk today about the property of limits stuff. And so we're going to do the 11 rules of limits. I'm going to show you some applications of those rules, and we're going to try to prove, to show a couple of them tomorrow. A couple of them that are relatively easy to show, but it's what is very important here is that you are actually going to use them whenever you need to calculate certain limits. So you don't have to go always through the definition, because these rules are so general that pretty much cover just about anything you can run into. Of course, there will be some limits that we will need to specially examine, but most of the limits that we're going to be dealing with within our class are going to be possible to do with these properties. So the properties are important, because once you learn them, you can apply them and calculate the limits without resorting to the definition. This epsilon delta definition we had last time is a definition that takes some time to understand, and then of course it's difficult to use in general cases. So we use that definition to prove these properties. So all of them hold, but I'm just going to list that for you. So the properties you see in the lecture, I'm just going one by one, and I'm going to show you how to use them. Right? So tomorrow we will prove a couple of them just in case, to have the understanding that all of them can be proved. Right? So the first property that we have about limit is that when you're taking a limit of a constant function, you know what a constant function is. So f of x is equal 3, for example. That's a constant function. The graph of that function in pre-calculus you've done, it's just a horizontal line. So y is always the same, regardless of what an x is. You pick up any x you want, and y is always the same. So the limit of that constant function, you can call it c. So that's the first rule. The limit of a function that is a constant when x goes to whatever x goes to is always c. Makes no difference where x is. Okay? That makes perfect sense. It's not really unexpected. The function for whatever the value of x is will always give you 3. So whenever x goes to the a number, the function, the y, goes to 3, because the function is not going to make any changes in terms of a y regardless of an x is. So this is perfectly logical rule. The another one, the second rule, about identity function. So this is a function y is equal x. The graph of that function is aligned symmetrical with within the first and the third quadrant. It's actually a line that passes through origin like that, right? So every x and y is the same. Okay, now when the x and y is the same, and x goes to something like a, where would y go? Yay again, right? Because the
Excuse me, Professor. Apparently no one is able to see you.
excuse me?
I don't think no one is able to see you right now.
Oh, you're talking about Zoom, right?
Yes.
You can see me on Zoom. Well,
No.
read on the top of the Zoom chat and read the announcement and I send you by email. I am on YouTube.
Okay.
Right? For all of you come a little bit later on Zoom, I'm gonna close the Zoom so I don't get the feedback sound. I'm gonna close the Zoom in 5 minutes. I'm still waiting, maybe somebody's gonna show up on Zoom. I'm on YouTube. So the link is on the top of the chat in Zoom. Link is also in the announcement. I'll send you a link in the email. Sometimes when I have a lecture that I consider to be a little more important to record and to write down in a better video, I'm gonna use Google Streaming. I'm not gonna use Zoom because Zoom is not having a very good videos for that. So plus of course recording in Zoom I have to upload on Blackboard, and those are huge files, and Blackboard is really slow. So I'm gonna use Google Streaming, and these lectures are gonna stay on the Google, on YouTube streaming. They're gonna stay there, just like every other video on the YouTube is gonna stay for a while. Okay, so you can if you didn't understand a piece of the stuff I was talking about it, you can just simply go there and watch again. And it's easy to watch, easier than on Blackboard. Yeah, you can talk back to me because this is the one-way stream only, but we can talk about it tomorrow anyway. So again, so we have two properties. One is for a constant function, and one is for identity function. The function that the y is equal x, right? When x goes to something, the y, the limit is about y. Y goes to the same thing. So this is really not a big surprise. Now we have the third property. Now this is a little more special. Okay, it says this: if f of x is equal to g of x everywhere, except let's say at 3 or wherever dx goes to, then limit of f of x when x goes to 3 or whatever else you want, so I'm gonna call it a, must be the same as the limit of g. As x goes to a. Okay? Now this is a nice property that you're gonna use very often. Okay? So it says, if two functions are the same, except maybe in that particular value, then the limit of one function and the limit of another function is the same when x goes to that particular value. Right? So that gives you idea that you can maybe simplify. If you have some complicated limits or some complicated function, maybe you can simplify to get to the function that is the same as the first function, but a simpler writing, then you can find the limit. Let me show you the idea. Okay, so I have limit of x squared divided with x as x goes to 0. It's just an example. So what am I going to do with that? I could use the definition of limit and try to find that limit. But I am going to use this property number 3. Because I know that x squared divided with x is actually x. Everywhere except at 0. Now, when we're talking about a 0, this guy here is undefined. Because you cannot divide with 0. You have a 0 squared divided with 0, so this is undefined. This one is defined, it's equal to 0. So these are not the same functions. This function here and this function here are not the same. They're different. The difference is because this one has a domain everywhere, all of the real numbers, while this one here cannot have a 0 in the domain. You can calculate this expression with anything except when you plug in 0. Now if you plug in 0, you cannot calculate this. Okay? So this function and this function are different. But they're everywhere else the same except the 0. So this fits this particular property. One function is equal to another function for all of the x's except 0. Now a is 0. Therefore the limit is equal for both functions when x goes to that particular value, which is 0 in this case. Right? So what I've done here, I simplify this into x, and now I'm going to use the previous property number 2. It says limit of x when x goes to 0 is equal 0. And I'm done. So I found the limit. Again, you can investigate this, and you put up lots of different values that are closer and closer and closer and closer to 0. You will find out that this is going to be closer and closer and closer to 0. Okay? So this is an important property we're going to use all the time. You can see the reason why we need this property is because we want to simplify the functions if we could do that. It will be beneficial. Okay, so this is property number 3. I am going to prove some of that tomorrow. Maybe this property number 3, maybe I'll prove that. Okay, the next property is also very important. We're going to use this property all the time. The next one. The next one says, what happens if you multiply function with a constant? Would you get anything different? And how is that different from original function limit if you make a multiple? Okay, so the property says like that. If limit of f of x, the function, when x goes to a, is equal an L, then limit of a constant time f of x. So you just multiply function with something, some constant number. It's just simply going to be c times L. So that's a property number 4. Okay? And I mean c to be any real number here. So we probably did that in the pre-calculus. C is any real number. 3, negative 2.7, negative pi, whatever you like. Okay? Now how do you use this property? It's very easy. Okay, here is an example. So I want to find the limit of the following function. Right? So I want to find the limit of 3x, function is 3x, so y is equal to 3x. You know this is a line with the slope 3 that goes through origin. You can graph it easily. So whenever you have an x, you just make a triple of that, and that's your y. And now what would the limit be? According to this, I just need to find a limit of x. We already know that's 2, because that's a property number 2, right? The limit of x, when the function is y equal x, is 2. So the limit of this is just the limit of a multiple is a multiple of a limit. 3 times the limit of x as x goes to 2, and the x, if x goes to 2, x goes to 2, y is equal to x, it goes to 2, 3 times 2, that's 6. Done. So you don't need any special investigation, you don't need to look at the definition of limit. There is a definition of limit at epsilon delta. You have to verify that if you really want to rigorously show that. But because of this property is much easier, because you're just recalling the property number 4. And then in the property number 4, you're also recalling the property number 2. This is from the property number 2. The limit of x when x goes to 2 is equal to 2. So I'm using two properties, number 2 and number 4. First of all, I'm using number 4 to fall back on number 2, and then on number 2 I just simply use that this thing is equal to 2. So it's 3 times 2, that's 6. Okay? Now I'm going to close the zoom because I don't want to have any background sounds. So I'm going to close the zoom. I hope everybody's right now on YouTube. Yeah, YouTube link. Somebody's still asking this question. YouTube link, so everybody come late. YouTube links or link is in the chat here, in Zoom, in announcement, and in your email. Choose which one you want to use. I'm going to close Zoom, so it's going to be now in your email or in announcement on the Blackboard. I'm closing Zoom. Okay? All right. I just want to check for a moment that people are on YouTube. All right. So this was a property number 4. So now, for now, I have the 4 properties of limit that I will use all the time. Now, very, very important one. Number 5. What do you do if you make a sum of two functions? You very often you do lots of different things with functions, like you multiply them with something. We just did that. You add them, you subtract them, you divide them, you multiply them. You also make a composite. That's a special story. We'll talk about that too. And you do lots of different things with functions that make composed function, or composite, I should say, the new functions. Okay. So sometimes you do sum or difference. So this property number 5 deals with the what if you do sum of two functions. And then the property number 6 is difference. So I'm going to write the property number 5 first, and I'm just going to quickly write the property number 6 after that. So if limit of one function as x goes to something, we're going to call that something a again, is equal L, and so there's some limit, some number, and limit of another function g if x goes to the same thing, so we're investigating this, the x going to do the same thing, is equal to k, then the question is what happens with the limit of a sum of these two functions. So if you sum two functions f and g, what happens with this sum if x goes to a? Okay, and the answer is very simple. It's just simply sum of two limits. Okay, the property can be easily expressed. This is kind of complicated what I've wrote in terms of a notation. It says if limit of one function is L, limit of another function is K, as x goes to the same thing, then the limit of the sum of two functions is just simply the sum of two limits. So you can actually say exactly that. A limit of a sum is equal to the sum of two limits. So limit of a sum of two functions is equal to the sum of two limits. How do you use that? Now here's an example. Let's say I want to find the limit of 2x plus 3 as x goes to, let's say, 4. Okay? So I see the sum of two functions here. One of them is 2x and one of them is 3. So according to this, I can split the limit. Limit of the sum of two functions is equal to the sum of limits. So which means I could just simply write limit of 2x as x goes to 4 plus limit of 3 as x goes to 4. Okay? sum of two functions. One of them is y equal 2x, another one is y equal 3. Okay? And I'll go back to the story I had moments ago. So moments ago I said the multiple, that was the property number, I forgot, number 4, says it's just simply the multiple of the limit. So this is, the first one here is 2 times 4. Again, I'm looking at the property number 2, because the limit of an x when x goes to 4 is 4. So limit of a 2x when x goes to 4 is 8. And this one here, that's the very first property we listed today, number 1. The limit of a constant, y equal 3 is 3. So the end result of my story here is the limit here is 11. Now you could say, well, you just plug it in here. Yes, but that's the next story, story of continuity. We'll talk about that. So when the function is continuous, but you need to know it is continuous. Yes, of course, I know this one is continuous because it's a line. But in general, if you want to just plug it in, the function must be continuous. So if you don't know whether the function is continuous or not, you cannot just plug it in. Right? I'm using here property, but it amounts to the same as it was just plugging in here, 4. 2 times 4 plus 3 is 11. Yes, but I actually use 3 properties. One of the properties about tackling the sum. So the limit of a sum is equal to the sum of the limits. That's what the property says. The limit of a sum is equal to the sum of the limits. The second property is about multiple, number 4. The limit of a multiple is equal to the multiple of a limit. So the limit of an x when x goes to 4 is 4. That's another property, number 2. And then the limit of a constant is equal to constant. So I actually use all of the previous properties. All of the 4 previous properties I have to get this result. And yes, it amounts to the same if I was just plugging in 4 here. That would be the same thing. But I was using property. There's a difference, right? The verification versus, what I feel I want to do. However, this feeling what I want to do, I just plug it in 4 here, is also okay. But that is only because the function is continuous. We'll talk about that as we go down the road. Okay, there is nothing special about subtraction. So the same thing about subtraction. So you can write the property number 6 would be I replace, and I wrote it that way, so I'm going to do it that way. I replace plus with minus, and the same thing applies. So the limit of a difference is difference of limits. So when you have 2 functions and you combine them into a new function, the way that you subtract, so the new function does, you calculate the f, you calculate the g, and then subtract those 2, and that's your output for a new function, the difference. The limit of a difference is the same as the difference of limits. So that is what this property says. And it's perfectly okay. We're going to use this again. I'm actually never going to prove this property because I don't have a time to prove all of those properties, but tomorrow I'll prove one for sum, so you can think about it, how would that work for a difference. By the way, you already know from the algebra that the difference is nothing but the sum with the opposite, right? So when you are subtracting 3 minus 4, you're just basically adding 3 plus the opposite, minus 4. So basically this particular property is not needed to be here at all. You could just simply go on and say, I have property number 5 about a sum, and I also have a multiple, property about a multiple, which is the opposite is when you multiply with -1. So that property number 3 and property number 5 combines for this property. So I don't need any special proof for this property, really. Okay? Now the next property is the product rule. Okay? Now, if you make a product of 2 functions, surprise, surprise, the limit of a product is equal to the product of a limit. Not a big deal at all. So, okay. However, this is completely new thing, and it takes some time to prove it. if you want to really verify that this is always the case, you cannot rely on anything I have done so far. So I had the 6th property before this one. You could not use any one of those 6 properties. I mean, you could use them, but you could not use them completely to be able to verify this. So this is brand new thing, and it's an important property that you're gonna use all the time. So let me show you this in an example. Let's say you want to find the limit of x squared plus 2x when x goes to let's say 3. So you have this function y is equal to x squared plus 2x, and you're looking for a limit of this function when x goes to 3. Now you can say, hey professor, I don't want to bother with that because this thing is known to me parabola. Parabola is continuous. I can just plug it in and I get the value. Yeah, that would be the case. However, I made a very simple function. That's why it's so easy. And just to show you how that works, okay? To be able to find this limit, I'm going to use first the property about sum, which is a property number 5. The property number 5 tells me that I could split this and write the limit of a first function, which is an x squared, and limit of a second function, which is 2x, excuse me. Okay? And I already know what the second one is because we tackled that moments ago. So the multiple, the constant multiple, is equal to limit of a constant multiple is equal to the constant multiple of a limit. So I already know that x goes to 3. So the limit of x when x goes to 3 is 3, and therefore this must be 2 times 3, which is 6. So that's done. So this thing goes to 6. Okay? Okay, I'm going to write an equal sign, of course. I don't want to use arrows because arrows don't mean anything in algebra, right? Okay, what about the first one? Okay, the first one is limit of an x times limit of an x. Why is that? Well, because of this property. The x squared is x times x. And limit of an x when x goes to 3 is 3. And limit of an x when x goes to 3 is 3. So the limit of an x times x when x goes to 3 is 3 times 3, which is 9. Okay? So I have here 9, 3 times 3 plus 6, which is 15. And again, it amounts to the same if you just simply, plug 3 in here. But again, plugging 3 in is a bad idea if you don't have a continuous function, because continuous function that is not continuous might not end up with a limit at that place at all. Or it could end up with a limit that is different than the function that you would get by just plugging in. That would be a different function. So again, I am using properties here. So the first property I use here is the limit of a sum is equal to the sum of limits. The second property I use here, I use this first, is the limit of a multiple is equal to the multiple of a limit. And I also use the property number 2, since the limit of an x is equal to whatever x goes to. Okay? If x goes to 3, the limit of an x is 3. And then I use this property here. So the limit of product of two functions equal product of two limits. So I got this first one, I got the second one. By the way, the same, because of course squared is when you multiply two the same things. And I got 9 for this, and I got 6 for this, and now I'm adding that to get 15. So I use a bunch of properties here. Let me see. I use the property number 7. The limit of a product is equal product of limits. I use the property number 5, the limit of a sum is equal to the sum of limits. I use the property number 3, the limit of a multiple is equal to multiple of a limit. And I use the property number 2, the limit of identity function y equal x is equal to whatever the x goes to. So I use 4 properties to verify this particular very simple example. Again, you could just say, you just plug in here 3. And you get 9 plus 6, it's 15, and you're done. Yes, because this is a parabola. The function y equal x squared plus 2x is a parabola. We studied it in pre-calculus. So we know it's continuous function. And a continuous function, the limit of a function is the same as the value of the function. And we're going to talk about that next week when we talk about the next week we'll talk about the continuous function. So what exactly is a continuous function and how that works when you are trying to find out whether the function is continuous, right? So that's the story for the next week. For now, your idea about continuous function is probably, I'm just simply making a graph, and I can just make the whole graph by one stroke on the paper, right? But that's not really mathematics. That sounds like art or something. Okay. Now, what about the quotient? So I need to have the rule that says what do you do with a limit when you have to divide two functions. So if I need to divide this function with this function, and there will be a new function, stuff is clicking on my board. So what will be the limit of f divided with g? Okay, so this is a new function. You make this function by dividing f and g, which means you calculate the f, whatever given x is, you calculate the f, then you calculate for the same x, you calculate g, and then you divide f with g, and that's your new function. You got it all the time, right? Rational functions, for example, are the quotient of two polynomials. So wherever you are looking for the limit of a rational function, you will have to be probably using this rule. Okay, so what happens when x goes to a? Now you could immediately say, I think most of people would immediately say, oh yeah, just simply, the L over k, I'm done. What does that say is that the limit of a quotient of two functions is equal to the quotient of two limits. Yeah, there is only one problem here. Okay? What if this is 0? Then you don't have it. You will not be able to have that. So we have to eliminate that case. So we say this rule works. And again, to prove this rule is very difficult. I'm not going to try to do that at all. And I'm actually going to say to you, if you want to prove this rule, you're going to have to read the textbook, because I don't want to waste my time in the class to do that. It will take a longer time to prove that. But it is true. So with one caveat here, we have to have a third assumption. So we have the first limit, we have the second limit, and the third assumption is, well, I can just put it together there, is that this one is not 0. Okay? So that's just an extra assumption, right? So the extra assumption here is that I can't have the k to be equal 0, because if I want to make this conclusion, I have to have something here, and if k is equal 0, I have this side undefined, so I didn't tell you anything about the limit. I'm just saying the limit is undefined, right? Which is not going to work. Okay, so that, again, what the rule says is that limit of a quotient is equal to the quotient of a limit, assuming that the second limit, or the one that is on the bottom, it's not 0. Okay? Now let me give you an example of this. And again, the story here is, yeah, well, I can just plug it in, right? And that's okay. You can just plug it in, you'll be okay. The kick is, this is a rational function, which is not continuous, but it is continuous around 2. And that's good enough, because you're only examining where x goes close to 2. So again, plug it in would work, but I have to repeat this again. The plug it in will only work if you can guarantee the function is continuous, or at least continuous around the target of an x. When x goes to 2, it has to be continuous around 2. So for example, I know that this is a rational function that is not continuous at 0. Okay? This function is not continuous at 0. If x is equal to 0, you get nothing here. As a matter of fact, this function, this rational function, has a vertical asymptote when x is equal to 0, which is exactly the y-axis. Okay? The kick is, when x goes to 2, I am not around 0, I'm around 2. And I also know that rational functions, any rational function, is continuous everywhere except at a place where it has a vertical asymptote. So it is continuous at 2. So what this whole story I just said amounts to, what this whole story amounts to, is that you can just plug it in. Okay? And again, I have to say that that's perfectly okay as a routine, as long as you are aware of everything I just said, that you're really dealing with a function that is continuous around 2. Now, if you don't have that, you should not make that plug it in. Okay, but I don't want to do plug it in. I am just going to show this property. So this property, let's verify. You have one function, that's my f, and you have another function. That's my g. Okay? What this property says, if you have a limit of an f, if you have a limit of a g, we'll check it out. Then limit of quotient of 2 function is equal to the quotient of 2 limits. So I'm going upstairs and find that out. And I'm going downstairs and find that out. So I'm using the property number 8. The limit of a quotient is equal to the quotient of a limit. Down there I already know that when x goes to 2, limit of an x is 2. That's a property number 2. So I have this rule of limits number 2 that I could use here. Okay? So I'm using a second property now. I already used this property number 8, and now I use the property number 2. Okay? Upstairs, I'm going to use 3 properties. The property number 6 would be that the limit of a difference is equal to the difference of a limit. So you can investigate limit of this and limit of this separately. That's the first property I would use. The second property would be, what is the limit of a 2x? We already did that. The limit of a 2x is 2 times whatever the limit of an x is. That's a multiple. That's a property number 3. Then, the limit of 5, what would that be? Limit of a 5 when x goes to 2 is 5. Because that's the very first property we had. Is the limit of a constant is the constant itself. It doesn't matter where x goes to. And then one more property I would use, because I would have to get a limit of an x. The limit of an x is 2. When x goes to 2, x goes to 2. So I'll be splitting this first as a difference, then as a multiple. Then I would find this limit, and of course I would find this limit. So I'm having here 4 properties until I reach conclusion that the limit of this would, so I can write this in piece by piece, like limit of 2x as x goes to 2 minus limit of 5 as x goes to 2. And then the next line, limit of a multiple is a multiple of limits as x goes to 2. What is this here? And then limit of, okay, stop writing this second one because I already know that this second one is 5. Again, I'm using the property about constant. And down there I already have 2. So the limit of an x when x goes to 2 is 2. So I have 2 times 2 minus 5 over 2. And lo and behold, I wrote too many things. I have negative 1/2 as my final answer here. Now I'm done with limits. I have just numbers. I have 2 times 2 minus 5 divided by 2 is negative 1/2. So the limit of this function is when x goes to 2, negative 1/2. And again, amounts to, all of this story here, amounts to plug it in here. But I didn't just plug it in because I don't want to play something that might not work. Right? Plugging in will work only when you're dealing with a continuous function at that particular target, around that target. That's a complicated concept. Okay? But I'm not using that complicated concept, but just simply using properties. Limit of a quotient is equal quotient of limits. Limit of a difference is equal difference of limits. Limit of a multiple is equal multiple of a limit. Limit of a constant is equal to the constant. And limit of an x, when x goes to 2, is equal to. And the rest is peanuts. I'm just simply calculating the final one. So I use, I don't know, I already forgot how many properties I use. Number 1 here, number 2 here, number 3 here, number 4 here, and number 5. 5 properties. I used 5 properties. Out of the 7 I had, out of 8 properties I already listed, I used, just to get that, 5 of them. Okay? This property is, by the way, extremely often in use. Okay? So I'll give you one example when this property is used with some other properties in the towel. I should. Well, I need the whole board, so I'm going to erase all of that. You're just going to have to remember that. By the way, of course, I didn't say that in this story here, the second limit, the limit of the bottom function is not equal 0, which is a condition here, right? Yeah, 2, it's not equal 0, so that was okay. Okay, so let me give you a little more complicated example. An example that you would have, if you want to plug it in, you would have a little bit of a problem, and the plugging in would not work. And that's going to happen in lots of places in your homework. Since I gave you already homework, in lots of places in your homework, their examples in the homework for problems are a little nicer. The plugging in doesn't work. What do you do then? Okay, well, obviously you're going to have to use properties. So I have this thing here. The first one is easy. So I have 2 examples here. It says x squared minus 4x divided with x minus 2. And for the sake of fun, we're going to have x going to 2. Okay? Because I want to make it the same way like the guys in homeworks are making. Plugging in is not going to work. Because you're plugging in on the top, you're going to have 2 times 2, which is 4. 4 times 2, which is 8. So you got 4 minus 8. On the top, you're going to get negative 4. On the bottom, you're going to have 2 minus 2, which is 0. So you're going to have to find this limit by plugging in, you're going to have to divide negative 8 with 0, which is impossible, right? So this is on the kind of example that plugging in is not going to work. Okay, so what am I going to do here? Well, we're going to use the property number 4, I believe. The property number 4 Oh, excuse me. The property, I forgot what the property is. Property number 3, yeah. Property number 3. Yeah. What am I doing here? Property number 3 here. You see property number 3. So if two functions are equal, then you can replace one with another when you're looking for a limit. If they are equal everywhere except at the target. So in this story here, in my example, these two functions, this function and the next one, I'm going to simplify. So this function and the next one I'm going to end up with are equal except at 2. Okay, what the next one I'm talking about? Well, I'm going to factor the one on the top. X minus 4. I think I copied something wrong. Let me see. Because I made example exactly that is an easy one to use. Yeah, I have 3 here. 2. Yeah, makes a big difference. Great. Eraser. Right. Makes a big difference, right? So, if I want to make this further, if I want to go any further, plugging in is not going to work again, because now the top is different. I don't have a square anymore. I made a mistake. I have a cube. So the plugging is not going to work, because you're going to plug in 2, you're going to get 8, you're going to have 4 times 2, which is also 8, so 8 minus 8 is 0, and then down there you have 0, and you have to divide with 0. Regardless of what you are dividing, you cannot divide. So you're dividing 0 with 0. That doesn't work. But I know the thing on the top can be factored. Okay? So I'm going to factor x first, and then I have an x squared minus 4, and down there I still have an x minus 2. And you can say, well, you didn't do anything, you just replaced the function with the same function, only you factor the top. Yeah, that's the whole point. Yeah, because I'm going to factor this further. So I have an x minus 2 and x plus 2. And you know that from pre-calculus, I mean, from algebra actually. This is really not that difficult, right? So the thing on the top is now what is called factored completely. You have only primes, prime polynomials on the top. Okay? And you can see this factor here, and this factor here can be cancelled. Now you can say in algebra, I'll just cancel this. No, in pre-calculus you must be aware what you end up with is not the same what you had before. Okay? You can say, how is this not the same? Well, it's not the same because I already was trying to calculate this when x is equal to 2. I was trying to calculate, it was my first idea, plug it in. I was trying to calculate and I come up with nothing because it's not defined. I have to divide with 0. But if I plug in 2 here, I have a 2 plus 2, which is 4, and 2 times 4 is 8. So I got something. So which means that this function here and these functions are not the same functions. This function does not have 2 in the domain. This function does. So there are different functions, yet they are the same everywhere else except at 2. Any other number, they will both calculate the same value, except 2. When you're trying 2, this function will give you nothing. This function will give you 8. So that's a big difference. So now we are using this property number 3, where we were able to have the limit of this function to be the same as the limit of this function, because they are the same everywhere except at 2. So that property number 3 allows you to do that. And now you're going to use this property about product, which is, I think, number 7. I should look at that, but it's number 7. What it says is that limit of a product is equal to product of limits. You don't even have to. You might even replace this with x squared plus 4, I guess. X squared plus 2x. or you can just do this. Again, I'm not going to multiply. It's not really that hard. So x goes to 2, x goes to 2. Now we already know the limit of an x when x goes to 2 is 2. The limit of this is the limit of a sum, so limit of an x plus limit of 2. Limit of 2 is 2. Limit of an x when x goes to 2 is also 2. So you have 2 times 2, which is, I already multiplied this, 8. And now you could say, yeah, this part amounts to plugging in. You could just plug it in here. Yeah, it is indeed the case, because this is parabola. It's an x squared plus 2x. It's a parabola. So a parabola is continuous, so you can just plug it in. Okay? So I come up with this limit to be 8. And again, not by plugging it in here. Because if I attempted to plug it in here, I would end up with dividing with 0, which of course I couldn't do, and therefore I wouldn't have any limit. Okay? So that's an important example to notice. Now I'm going to give you one harder one. So I have a harder example, something that looks like problems in your homework, which are harder. And you're going to have to really work them hard. Okay? It will require a serious amount of algebra. Why am I having problem cleaning the board today? Maybe it's too humid, I don't know. Something, right? So my next example is kind of difficult. It involves the radicals, and that's always a big problem. Say I have the x on the bottom, and I have radical of 2 plus x, and then the other one is also radical of 2. And to have fun, of course, I'm going to let x goes to 0, right? Because I don't want you to plug it in, right? The first immediately will notice I can't plug it in, because if I plug it in, I have down to 0. I will be dividing with 0. I'm not going to be able to come up with anything. So you ask, what do I do here? This is a perfectly legitimate function. There's nothing wrong with that. What's the limit of this function when x goes to 0? One way to do that, you know, when people have no better idea than usually do the guessing. One way to do that, try to get something close to 0 and see what this turns out to be. And then try to get it closer to 0. You have a calculator and see what this turns out to be. And try the third one, and fourth one, and fifth one, and see. Maybe you'll come up to some number. Right? Maybe there is some number. The most stupid way to do that, because some people will do that in the test when they get a problem like that, is just going to write 0 with it. Like a limit when x goes to 0, the whole function must be also 0. Nope. Actually, that is not going to be the case here. And you will never guess the result here, because the result is not even rational. So it's not even a fraction. And you wouldn't be guessing fraction either. But you will definitely not going to be able to guess the result here. So you're going to have to do work here. What work can you do? Well, if you don't have any better idea, you can kind of remember stuff you're doing from algebra. In algebra, factorize. There's nothing to factor here, so forget about that. Rationalize. What did you do in algebra? That's why you study algebra, so you can get those different ideas. Maybe you can change this a little bit. Rationalize denominator. Well, you don't have a root in denominator, so you can't do that. I mean, it's already rational. It's not radical. You have a root in the numerator. Ah, okay. Let's rationalize numerator. I don't know whether I'm going to get anything useful, but let's try to do that. So this is the idea from algebra. I know something I can do with the fraction. Let's see, maybe I can change that. And let's see, maybe that's going to work. That is the goal here. So I'm not going to write a whole new line for that. I'm going to multiply up and down with the same thing. This should be familiar to you from algebra. Okay? So I'm guessing this is familiar to you from algebra. This, by the way, is 1. Somebody is sending me email. We'll disregard it. So this is 1, which means if I multiply this thing with 1, I am not changing the function. This is the same function as before. I'll just make it look more complicated. You can say, okay, so what do you accomplish with that? Well, I don't know. I'm just changing this. I'm rationalizing numerator and see what that leads to. Maybe I can get it something simpler. Right? Sometimes when you make things that you don't know why you are making them, could turn out to be more complicated, turn out to be simpler. We'll find out. But since I don't have any better idea, I'm doing that. Okay? Now I have to multiply. And the reason I have, so, radical minus radical, radical plus radical. What happens when you multiply a plus b, a minus b? You get a squared minus b squared. Okay, so the square of this minus the square of this. Okay, that's the top here. Again, I'm using the formula a minus b, a plus b. When you multiply, you get a squared minus b squared. The square of a, the square of b, subtracted. Okay? That's the top. That's the whole point of rationalization of anything. You rationalize, so you multiply. This is minus here, it's a plus here. We're going to turn out to be a squared minus b squared. Down there, you have nothing else but you have to multiply. Nothing special happens here. It's just multiply x with this stuff here, which is... Okay? By the way, rationalization of numerator or denominator is often done in calculus. So that's one of those tricks that you learn in algebra that in calculus we use all the time. Okay, I can simplify the top. You can see I have 2 minus 2, so just an x left. Okay, x still goes to 0. Sometimes people forget to write this piece here, and they write just limit and then further on, which is gibberish, because you need to know where x goes to. So don't ever forget this. X must go to something. Okay. Oh, now I see I can cancel x and x. That's that benefit you didn't expect, right? Okay, that's great. Because what I'm gonna getting now is 1 over radical 2 plus x plus radical 2 when x goes to 0. So you can say this guy and this guy are the same except when x is equal 0. When x is equal 0, this guy is undefined because you have to divide 0 with 0. This is some number here, but who cares? This is 0, so whatever this number is 0 times something is 0. So you have to divide 0 with 0, so this one is undefined. This one, when you plug x equals 0, you got actually something. So they are not the same, this guy and this guy, two different functions. This function and these functions are not the same, but they are the same everywhere when x is not 0. So everywhere around, they are the same, but at 0 they're not the same. And we are allowed this property number 3 to replace the function with another function. So this one with this one, and then the limits are the same. That's property number 3. Okay? So again, you can say, I'll just cancel this x and x. Yeah, you can do it in algebra, but not in pre-calculus. When you cancel, you get a different function. I mean, the expressions are the same. I mean, not the same, but the expression kind of, they have, you know, everywhere else the same except when x is equal to 0. So which means that functions are not the same, because then one has something in the domain that the other one doesn't. And that's a big difference. The function have to be the same. If they are the same, they have to have the same domain. So what's the whole point now? Well, the whole point is here that you can just plug it in here. If you plug it in x equals 0, you get the radical 2 and radical 2. You have 2 times radical 2. And you can rationalize this again. You multiply up and down with radical 2, so you get radical 2 divided by 4. Or you can keep it this way. Doesn't make any difference really. This is easier to calculate if you need to do that manually. So if you multiply this whole thing up with radical 2 and down with radical 2, you're going to have radical 2 times radical 2, which is 2 times 2 is 4. And upstairs you're going to have 1 times radical 2, which is radical 2. So you can do that. This and this is the same. You're done here or here. It doesn't make any difference. Other than the second one is probably nicer, because it's easier to calculate. If you are manually required to calculate, it's much easier than to calculate this. The calculator doesn't have any problem with either. Okay? So you can say, wait a moment. At this point you were plugging in. How do you know you can plug it in? Well, I know that this function is continuous. Okay? We'll talk about it later. I mean, not today. Further on in the course. You can also, if you don't believe me, you can use the properties here. The property number 1 would be, you have something on the top, when x goes to 0, this goes to 1. It's going nowhere really, it's always 1. And something on the bottom. That's the property number 8. The limit of a quotient is equal to quotient of limits. So you can do that. And then you have to examine the limit of, so I'm writing something separately here. You have to examine the limit of 2 plus x plus radical 2 plus x plus radical 2. Okay? What happens with this when x goes to 0? Okay, now you can use the property that allows you to say that limit of a sum is equal to the sum of the limits. So basically, this is a constant, radical 2. So that's just radical 2. So I don't have to worry about it at all. You really have to show what's the limit of this guy. Now, if you can show that, that of course is radical 2, but plugging in. But really, you have to show that limit of this is equal to something. Okay? The story is, I'm going to show you that in a moment, there's going to be property number 9. I didn't yet do that. Limit of a radical is equal to the radical of a limit. That's an amazing thing. Okay? So here I'm replacing limit of a radical is equal to radical of a limit. I'm replacing the order of operation. One operation is a finite operation, taking a radical, finite algebraic operation. The other is infinite operation, taking a limit. Can you switch the order? Right? The order of operations is not the same. Limit of a radical is equal to radical of a limit. It's a difference. The first limit, then a radical, or first radical, then a limit. The rule is yes. And I am going to list it as a separate property. Okay? I should have done that as a property number 9. I just simply forgot to list it. It is in the paper, in the lecture. Okay? Now you're done. Because now you have a limit of a sum, the limit of the first one, limit of the second one, a limit of 2 when x goes to 0 is 2, limit of the second one when x goes to 0 is 0. Limit of an x when x goes to 0 is 0. This is, I think, rule number 2 or something like that. Okay? So that means the whole thing here is radical 2. So that way, yeah. So you can actually show that this is okay to plug it in. Okay? So there is one property that I just simply overlook. I didn't really write it down yet. And this is a very important property that we are going to use. And I already used this in this example. The limit of an x, f of function, when you have some power of that function, let's call it k, when x goes to an a, so this is property number 9, the limit of a power of a function is equal to the power of a limit. So let's put limit inside. Okay, and again, this is the power first and then a limit. And if you're confused because we haven't never done order of operation for limit, you can write like that. Power goes first and then the limit. Here, limit goes first and then the power. So this property tells you can reverse the order of operation of a power and a limit. Assuming, of course, that you have a limit of an f, right? Because if you don't have a limit of an f, if this is not defined, then you don't have anything here. But the property is not going to work. All right? So that's what I use here in the previous example, because a power of 1/2 is a radical. Square root is a power of 1/2. Right? So this works for any k, provided it's a real number. Okay? Now, this particular property actually is extremely hard to prove. You need to study more of mathematics that you will ever study. Most of you. So I'm not even going there. But the property holds. The limit of a power is equal to the power of a limit, which means that the order of operation of power and limit can be replaced. So when you're dealing with the radical, and you're looking for a limit of a radical, you can say it's the same as the radical of a limit. That is a very important property. You're going to use it all the time. Let me show you that on one other example that I don't have in the lecture, but it's an example that is of some importance. Because that would be an entry into proving property number 9, which we are actually never going to attempt to do. So we're never going to be proving that. Jeez. For some strange reason I can't use my erasers, so I have to erase more differently. Maybe I need to change the board. All right. So limit of an x squared when x goes to, let's say, 3. We already did this today. So we say, hey, you can just simply use a product property. The product is the x times x. Then x squared is x times x. So you have a limit of x times limit of an x, right? When x goes to 3. And then you're done. The first one is 3, the second one is 3, 3 times 3 is 9. Basically, you're plugging in. But you can now use power. So, for example, if this is 4, that product rule would take some time, right? Because you're going to have x times x times x times x. Now you're going to split the first 2, the second 2, and you go. But now you can use this limit of a power is equal to power of a limit. So that's a property number 9. Limit of a power is the power of a limit. And limit of an x when it goes to 3 is 3. So you have a 3 to the power of 4, which is 81. So this amounts to plugging in. I know. You're going to say, why don't you just plug it in? Plugging in means that you are telling that the function is continuous. I do know that this function is a polynomial. I know polynomials are all of them are continuous. So yeah, you can use that in this particular case. However, if you run into the function that is not a polynomial, for which you don't know whether it's continuous or not, you cannot just simply plug it in. Because the plugging in is only when the function is continuous. We're going to talk about it separately. We have a separate lecture on that. Okay? We have more. We have something called comparison with squeeze theorems. Now those are special things, and we're going to use them all the time. All the time. When we are dealing with the functions which are so bad that we can do nothing else, that algebra is not going to work, and you're going to have to be able to do investigation of a limit anyway, whether you have an algebra available to you or not. Right? For example, let's say cosine or sine function or tangent or stuff like that. What algebra you know that? Nothing, right? The only stuff you know about these guys are the trigonometric identities, which are very important, and we're going to use them, but there's no any algebra there that can help you to find limits of functions like that. And there are very often functions. You have a whole pre-calculus you were studying those functions. Okay? So we need to have more than just algebraic properties. So far, all of the properties I have are algebraic. Limit of a sum is equal to sum of limit. Limits of a difference equal sum of difference of limits. The limit of product is equal to product of limits. The limit of quotient is equal to quotient of limits. The limit of a power is equal to power of a limit. The limit of a constant is equal to the constant. The limit of an x is equal to whatever the x goes to. A limit of a multiple is equal to the multiple of a limit. All of them. I think all of them. There is only one, property number 3, which is not an algebra property. It's like says, if two functions are the same everywhere else except in the target of an x, then the limits are the same when x goes to that target. That's not an algebra property. But the rest of them are all algebra property. You talk about multiplication, addition, subtraction, division, power, and stuff like that. It's all algebraic operations. Okay? Now, the following property number 10 is not an algebra property. It talks about functions. So it says if f of x is less or equal than g of x. So I'm comparing two functions. One of them is the bigger function, one of them is a smaller function. On an open interval. Now this is very important. This is a topological notion. It's nothing to do with algebra. About A, some number A. What does that mean? If the number A is 3, then open interval around 3 could be something like from 2.5 to 3.5. Anything that includes 3 inside, not on the boundary. So it's not open interval would not be from 3 till 4, because 3 is then a boundary there. It has to be inside. It has to be open around 3. That's what we say open interval, meaning an open end. Like, so you have a 3 and you have something between 2 and 4. That's an open interval between 2 and 4. I'm not looking at 2, I'm not looking at 4, I'm looking at the numbers between 2 and 4. 3 is in there. It's in that open interval. So you need to have that. Okay? So, if this is so, then the limit of an f when x goes to a is less or equal than the limit of a g when x goes to a. This is so natural that most of people have zero problem with this property. Yet it requires a proof. It's not given. So again, this is the property that is not algebra property. It says if two functions are in this relation, that one of them is bigger than the other or one of them is smaller than the other, then the limit is in the same relation. The limit of the first one is smaller than the limit of the second one. Okay? It makes perfect sense, because if x goes to a, whatever the x is, f is always smaller than g. So it has to be that whatever f is reaching must not be bigger than what g is reaching, because g will always go above f. Now notice I didn't write here strictly bigger, I just wrote bigger or equal, so that's perfectly okay. So that makes perfect sense. If x goes to a, f is always smaller than g, so whatever the target of f is must be not bigger than the target of g. This means not bigger, right? Doesn't mean smaller, it means smaller or equal, which is translated in the common language, not bigger. So if f is not bigger than g, then the limit of f should not be bigger of limit of g. Okay? And this is extremely important, that a, the target of a, of x, the target of x, must be included in some open interval, and this is always true. Okay, because I can give you a counterexample when if you're missing this, that conclusion will not hold. And that's a really pathology of mathematics. So this is a non-algebraic property, and yet it's a property that we will use. Okay? There is also a squeeze theorem property, and this is extremely important one. It's very, very much related to the first one. Okay? It says this: if f of x is smaller than equal to g of x, and that is also smaller than equal to h of x, so which means that g is sandwiched. That's why it's called sandwich theorem. G is sandwiched between f and h. So there is one function that is smaller and another function is bigger than g. And again, it has to happen on an open interval. Around about A. We're also going to ask two more. And if f and h have the same limit, let's call it L. Just, I don't have the, what happened to my razor? I have no idea. I'm going to have to clean it, I guess. So what I'm saying here, I have two conditions. First condition says these three functions are in this relation. G is sandwiched between f and h on an open interval around the target of an x. Okay? So if x is 3, somewhere, let's say, between 2 and 4, I'm not saying there has to be between 2 and 4. It can be between 2.5 and 3.5. It can be between 2.8 and 3.2. Any open interval you like. It doesn't even have to be symmetric. It could be between 2 and 3.1. But it has to be an open interval around target of an x. These three functions must be in this relation. This guy is going to be sandwiched between these two. And the second condition I'm asking is that f and h must be with the same limit. Then since this guy is above and this guy is below and they are both reaching the same target, then the one in between must reach the same target. So the conclusion is very important. Then limit of a g when x goes to the target is equal to the same thing, L. If you can sandwich one function between two other functions that have the same limit, then the one in between must be going to the same limit as well. This is called a sandwich theorem or a sandwich property. In United States, it's also called squeeze theorem. So use it either one you like. I'll use both. Squeeze theorem. How you're going to call it doesn't make any difference, really. I mean, this is what it is. You can just call it property number 11. That's how I wrote it in my lecture. But if you look at the textbook, it might be something else. It's probably called squeeze theorem. That's how it's called in the United States. Squeeze theorem. You have a theorem on squeeze. So these two guys are squeezing G around the target of an X, and because they have the same limit, this guy that is squeezing between must be the same. Like you're sitting in the car, you know, two guys are on toward the doors, the guys is in the middle, and they are squeezing, and you know the the car travels somewhere, this guy in the middle will not gonna be able to get out anywhere, so he's gonna go exactly where these other two guys are going. If they are going to the same place, he will have to go to the same place. That's it. That's the logic of the whole property. It's not really that difficult to conclude. Now, I would like to use that squeeze theorem to show you something that we consider to be a very important limit. Okay? Yeah. Where is this popping up? All right. Take a look at this. What I'm trying to find out is what's the limit of a sine x divided with x if x goes to 0. And so, the first thing you need to notice immediately is that plugging in will not work. Because on the top you have a sine x. When x goes to 0, the sine x goes to 0. You can check it out. I mean, sine of 0 is equal to 0. On the bottom you have, if x goes to 0, the x goes to 0. So you have 0 on the top, 0 on the bottom. If you divide 0 with 0, you will reach nothing. You can't divide with 0. That's just that. I mean, the top is irrelevant. The bottom is 0, so you cannot divide with 0. Plugging in is not going to work. So, next thing you can ask yourself, okay, if the plugging in doesn't work, can I simplify this? Okay, first of all, simplification with algebra will not work because sine is non-algebraic function. That's how we call it. We call it in serious mathematics a transcendental function. It's how we call the functions that are not algebraic functions. We call them transcendental. Okay? So I don't know any algebra that can do that. Maybe I can actually do some trigonometric identity that could simplify sine of x. An intelligent person is going to immediately say, sine of x is as simple as it gets. You can't get it any simpler than that. So you can try, but it's going to be a waste of time. You're not going to be able to do anything. All right? So the question here is, what am I going to do with this? Okay, nothing really. We're going to use a sandwich theorem. So, sandwich theorem, property number 11. So, I want you, because we're kind of almost out of time, we have like 3-4 minutes left. I want you to read this. You can notice that I was able to sandwich a sine of an angle, and you can call it angle x, you can call it theta. When I have a picture, I could rather call it theta, but you can call it any way you want. I was able to sandwich sine between a 1 and the tangent, and then I was doing some fancy work here to get the oh, excuse me, no sine. I was able to sandwich the sine, the angle between the sine and the tangent. And then I was doing some fancy algebra work. I was dividing something. And at the end of the story, down there on the bottom, you can see that I get the sine of an angle divided by angle, which would be sine of x divided by an x, sandwiched between the cosine and 1. So I want you to check it out, whether this holds. And then, of course, I need to tell you that the cosine is a continuous function, which you already know, I guess, and that the limit of a cosine therefore would be the same as the cosine and whatever the limit you're looking at. So the cosine of 0 is of course 1. So the one in this sandwich on the left goes to 1. The one on the right, which is 1 in this inequality, also goes to 1. So the sine of x over x, or the sine of theta over theta, actually must be 1. by the squeeze theorem, by the sandwich theorem. Okay? So I'm using here sandwich theorem, I'm not using any algebra here. I use some algebra because I started first with an angle being sandwiched between sine and tangent. And then I was doing some little algebra over there to flip this around and to get the sine of theta over theta sandwiched between the cosine and 1. So I want you to read this. I didn't really, prove that. I just was kind of explaining the idea, what I was using here. We will do that tomorrow, okay? And we will do 1 or 2 more proofs tomorrow. Okay, so tomorrow we have a Zoom class. I'm not gonna do the YouTube streaming. I'm gonna do a Zoom class. So tomorrow we're gonna have a Zoom class in which I have now 11 properties, and I am going to prove, let's say, 2 of them, and I'm going to show you this one also. But I want you to think about that yourself. And the story goes on that I might do a couple more examples if I have. You can see I have a couple more examples if I have the time tomorrow, or I'm going to ask you to read this yourself. Okay? I think I'm going to do a couple more examples tomorrow because I have an hour and 15 minutes. I'm definitely going to be able to do that. So I'm going to do that couple more examples tomorrow, and then you have a nasty homework. I have to say, this homework number 3 about the property of limits are not an easy homework at all. You're going to test yourself how much you know. Okay? So I'm done. We are done with the class. I am going to stop streaming, and I am going to let this stream stays on YouTube. So if you want to watch this later, you can just go to the same link. A link is, again, if you don't bookmark it, it's in the announcement, and it's in the announcement on Blackboard. You have it in your email, so you go there. I see you tomorrow on Zoom. Make sure you write down any questions you have right now. I know you can talk on YouTube, but you can write down questions you have, and we meet tomorrow in the morning again, 9:30. So you can ask me tomorrow. So I have my tomorrow plan is to go to this lecture again to try to prove 1 or 2 property I had there from 1 till 11. Will not prove the squeeze theorem, but will be actually I could do that, but I'm not going to do that. And I'm going to do this sine thing, the example, and a couple more examples. So that's the plan for tomorrow. And if you have any questions, yeah, you can ask me any questions. Homework is going to be really nasty, but I don't expect you're going to ask me that tomorrow. I think you're probably going to ask me about it next Tuesday we meet. Try to do the homework. You'll find yourself in lots of nasty algebra there. That's how the guy, and I didn't give you the hardest problems. There are problems there that in the textbook that are harder than the one I put in the homework. So I gave you kind of like mild to moderate problems there. Try to do it. Okay? I'll see you tomorrow in the morning. I'm stopping streaming.